Hey guys, welcome back. Today let's discuss this problem called minimum time to collect all apples in a tree. So here we're given a tree and the nodes are numbered starting from 0 to n minus 1, and the value of n is also given as an input. And at each node we have a boolean which tells whether it has an apple or not, and the task is to go around and retrieve all of these apples. And in going from one node to the other, we take 1 unit of time. Here it is mentioned as seconds, and the challenge is to do this in the minimum possible time, and that minimum time is what we have to return. So for instance, here they've mentioned they've given the path, the optimum path. So you go like this: pick up 4, then you pick up 5, then you pick up 2, and in total you make 8 steps, which takes 8 seconds, and so on. So this is the problem, and I already have my solution, so I'm just going to make that large. So you can pause, and if you understand this, then I guess there's no need to watch the video, right? So initially I had a few doubts regarding this question. For instance, here it is mentioned from I is less than 2i, but in the question there is no mention of from or to. So I thought maybe it means AI is less than BI, and it turned out to be that. But it could, initially I thought it also meant that whatever value which we have as parents, those will be smaller than the values of the children, or the indices of the children, because in both of the examples that have been given, here we have 0, and then it has children 1 and 2, and then 1 has children 4 and 5. So it seems like at each level, at each height, as you keep going down, the numbers keep increasing, and it's the same with this case as well. So I had made that assumption, but it turns out that is false. So it is entirely possible to have something like this, where you have 0 here, and then 2 and 3 as its children, but 2 can have 1 as its child as well. So the only thing that is guaranteed is that when you get these edges, and edges are given as a list of 2 indices, which means there is an edge connecting these two. So 0 and 1 are connected, and so on. So it just means that the first value is going to be less than the second value, but I don't think that's very helpful. So we now have this tree, which is the one given in example 1. So we have 0, 1, 2, 4, 5, 3 and 6, and 2, 4 and 5 have apples. So the question mentions that we need to start from the root of the tree, which is the node having, or the vertex 0, and then collect all apples, and then come back to vertex 0. So if we take any vertex which has an apple, and if we imagine that that was the only apple present, then what would we do? So for every edge that connects that node with its parent, we can count 2 seconds for every edge. So let's say 4 was the only apple that was present. Then what we would do, we would come down till 1, 1 to 4, and then we would collect an apple, and then we would go back up. So we have 2 edges here, and for each one we can count 2 seconds, one for coming down and one for going up. Now if I were to do this for every vertex which has an apple, then I would end up counting it twice. For instance, if I had 4, if let's say I came across this vertex first, and then I had already counted it, then when I count it again for 5, what's going to happen? I will end up counting this part 2 times, right? So I need to count only the additional steps that need to be taken in order to fetch this apple from 5, which is only this edge. Now when we come to 2, there's only one edge until we reach the root, so we can count that too. So my solution is basically a generalization of those steps which we just discussed, which is you take the nodes having apples and then you traverse the tree upwards till you reach the root, and then for every edge you count 2 seconds. And in addition to this, to make it work, we need to keep track of which vertices have already been visited while doing this counting. So for instance, if I started with 4 and then let's say I'm just crossing out the ones which have been visited, right? So then for the rest of the vertices which have apples, if I do the same thing but I stop when I reach a vertex which has already been crossed out, meaning which has already been visited, then I will count it correctly. So here I would count it only once, then I would mark this as visited. Then when I come to 2, I will count it correctly and I will cross this out. And this would have worked if we had taken it in a different order. So if I came across 2 first, then I would have counted this, so that's fine. Then if I had come across 5 secondly, let's say, then we would have counted these two, right? And then when I come across 4, I would count only these 2 steps, so that would sum up to 8 still, which is correct. And if we check this, it would work out in any order. And let's say there were more vertices with apples, let's say. So let's say there was one more here, and then let's say there was one more here. So same way, and let's say we came across that after we had seen all of these, then it would just add these 2 steps, or rather 4, right? So this is the algorithm. Now coming to the implementation, what I've done is I've used an array or a list to keep track of the parents. So I have a variable here called parents. So parents of I simply gives the parent node to the ith node. So for instance, parents of 2 would be 0, parents of 3 would be 0, parents of 1 would be 2, and I'm using none to denote that there are no parents above it, meaning it's the root node. So parents of 0 will be equal to none. Now, as we've mentioned earlier, there's no guarantee that when we get a pair A comma B as an edge, there's no guarantee that A is the parent and B is the child. So in all the examples that we've got, I think that is the case, like 1 comma 4, 1 comma 5. So the parent is usually given as the initial index, but there are cases where it's not, and yeah, this guarantee is not given in the question as well. So we need to take care of how to figure out which one is the child and which one is the parent. So what I've done, I've initialized this list to have -1 for all of the indices except for 0. So here I'm making an assumption that when we get edges, we get the ones which are higher up in the tree first, and only when all the edges at a certain level have been listed, then we get to the edges which are below that. So for example, in this case, we would get this edge and this edge first, and only then get edges below this level. So we would get the edges at this level first, and then the ones at this level, and so on. So I've made this assumption. So if this holds, then what we can do is we'll know that these edges would already have appeared first in the list called edges. So for those, the values would have been set. And when we get the initial set of edges, there too this logic works, because let's say instead of getting 0 comma 2 I got 2 comma 0. Even then this would work, because only 2 would have -1 set, because I've already set the value of parents of 0 to none. So from then on it would start adding parents of 2 equals 0 and parents of 3 equals 0. So anything that comes below this, which of the nodes does not have the parent set, and that would be the child. And so the parent would be the other value. That is what I've done here. And we have the parents list complete. Then what I do, I go through the has apple list, and if it does not have an apple, I skip it. If it has an apple, like in this case the vertex 1, I keep going up until I reach the root node. So here I've used the condition of checking if the parent's value is none, which is true for the root node at the beginning. So I'll keep going up, and then in addition to that, what I do for every node which has been visited, I'm setting its parent to none. So essentially later on, let's say I found this node vertex 1 and I've traversed till the root. So for later values, let's say there was something below this. Now from here, when I go back up and check parents of 1, it would be none, because while going up I've set the value of parents of each of these to be none. So for if there was any node below this which had an apple, it would only count till here. So that ensures that the count is not duplicated, and that's basically it. Now if we submit and check, yay, it works, and apparently beats 100%, so that's awesome. So that was my solution to this problem. Thanks a lot for watching. See you guys in the next one.